Okay, section 2 is the rational numbers. So we are sort of working our way towards the real numbers. Right? We started off with the natural numbers, right? 1, 2, 3, etc. Right? You can talk about what follows the natural numbers is usually the integers, right? 0, 1, -1, 2, -2, etc. Right? The integers, and then you have these things, the rational numbers, right? Rational numbers are things that look like m over n, where m and n are integers, and the denominator is non-zero. Right? So these are the rational numbers. Okay. And we're basically assuming that you know what the rational numbers are, but the things that look like m over n, where m and n are integers, right? So anything like 31 over 10, right? 1 over 2, 5 over 4, but not pi over 2, right? Not pi over 2 because pi is not a rational number. Right? Okay, so anything that looks like this, these guys are rational numbers. Okay, so basically each step upwards remedies a problem with the previous. So here, if you're stepping from n to z, the problem is that if you subtract 2 from 1, then you get something that's not in the natural numbers, right? You can make so you can say 1 minus 2 equals what? Well, there's nothing there, and so you say, okay, well, stepping up to here remedies that gap, and then for here you say, well, I can't if I multiply by 2, I can't, if I say something like 2 times what is equal to 1, right? 2 times what is equal to 1, right? There's nothing that solves that equation, but if you step up to the rational numbers, then you get these you get the multiplicative inverses. So here, what you're getting is basically what are called additive inverses, and here what you're getting are multiplicative inverses. Okay, and so stepping from Q to R is actually a little bit more complicated. Like the question you could ask, like what gap do we fill in going to R? Right? What lack do we remedy? What lack do we remedy? What's bad about Q? What's so bad about Q? They used it for a long time before. Okay, so here's one problem that the Greeks noticed. In Q, no number solves x squared is equal to 2. No number solves x squared equals 2. Right? There's no square root of 2. And so this arose for the Greeks in considering the following question. They said, well, suppose you have a right triangle with side lengths 1, right? If all numbers are rational, what's the rational number? What's the rational number that expresses this third side? What's the rational number that expresses this third side, right? And say, well, you could say, so you observe that x squared is equal to 2, right? This number here, let's call it x, right? The square of x is going to be equal to 2, right? Either you observe that by the Pythagorean theorem, or you observe it. It's actually in one of Plato's dialogues, Meno. If you look at Plato's Meno, they have Socrates talking to a slave, and Socrates is trying to show that every person has some sort of innate knowledge of mathematics, and he calls up just a random slave and he starts badgering the slave with questions, and he says, well, what would you do? What is the square of this length? And he just asks the slave more and more questions, and he draws out the following picture. He says, well, look. Suppose we take 4 copies of this. Suppose we take 4 copies of it, and you see that what's the area of this object in the middle, of this square in the middle? Well, the area is x squared, right? The area is x squared. Right? The area here is x squared. But you also see that that these lengths, what's the total area of the big square? Well, the big square has area 4, right? And you see that this thing here is half of the total area, right? So that x squared is going to be half of 4. In other words, 2. Right. So that's how Socrates does it. Okay. So but it turns out, so the Greeks had this question, right? What number, if all numbers are rational, what rational number's square is 2? And eventually they were able to see that if x squared equals 2, then x cannot be rational. Right? There is no expression of x as m over n where m and n are integers and n non-zero. So this was a famous result. It basically showed the Greeks that their number system had holes in it, and the story is that the Pythagoreans killed the person who discovered this, who came up with this proof, because it overthrew their whole system of the world. Right? So the story is, and I don't know if this is actually true or just some story. The story is that the Pythagoreans considered all things to be based on rational number. And so when one person came up with this proof that here's this number, here's this length, and it's not a rational number, it was very upsetting to them. Okay, so this is a famous proof. Let me show it to you quickly. Okay, so proof. Suppose x is rational. Suppose x is rational. In other words, x equals m over n for some m and n in the integers where n is non-zero. Okay. And we can assume that there are no common factors in m and n. Okay, so if they have some common multiple, factor that out, right? Cancel that out. Okay. Okay, so then, in that case, then m over n quantity squared is 2, right? X squared is 2, so m over n squared is 2. So that tells you that m squared over n squared is 2. Right? So that tells you that m squared is equal to 2n squared. Right? Okay. Now, so that tells you that 2 divides into m squared, right? m squared is even. M squared is an even number, right? So 2 divides. So this is divides evenly into. Right. 2 divides m squared. Okay. 2 divides m squared. If you know that 2 divides m squared, what do you know?
N squared is odd.
N squared is odd?
No, sorry. M squared has to be.
M squared has to be even. Okay, so m squared is even. Yeah. And actually, you can say something. Can anyone say anything a little bit better than that? M squared. Suppose you know that m squared is even. What can you say about m?
M has to be even.
M has to be even. Great. Right. In fact, m has to be even. Okay. Maybe that needs a little bit of proof. So let's maybe put that y. If m is odd, say m is 2k plus 1, say, then m squared would be 2k plus 1 squared, which is 4k squared plus 4k plus 1, right? Which is odd. Right? So if you're odd, then your square is odd, right? If you're even, your square is. I'm sorry. If your square is sorry. Sorry. If so, we're proving the contrapositive here, right? That right. So if m squared is even, then m must be even. M must be even. Okay. Okay. So m is even. In other words, m equals 2k for some integer k. Okay. But then we see that coming back to here, 2k squared equals 2n squared, right? Because m squared is equal to 2n squared. Okay. Does anybody see where we're headed with this?
We reach a contradiction.
We'll reach a contradiction. What will be the contradiction, Marco?
Well, we will have a common factor.
Yeah, we'll end up with a common factor. So you see what's going to happen. We get 4k squared is equal to 2n squared. In other words, 2k squared is equal to n squared, right? So what does that tell you? Right? That tells you that 2 divides n squared, right? But from what we said over here, if 2 divides n squared, then 2 divides n, right? Right, and so you get, so m and n are both even. So what you get is that, so if we assume this x is rational, equaling m over n, we get that m and n have no common factors, And we also see that m and m have common factors. Right? So that's a contradiction. Right? That's impossible. That's impossible. So, right? So thus, x could not be a rational number. So this is the contradiction mark. Okay, so this is an example of something called proof by contradiction. Proof by contradiction, in case you haven't seen it before. Proof by contradiction, right? You're trying to show, close your eyes for a second. Everybody close your eyes for a second. Raise a finger if you haven't seen proof by contradiction before. Okay, open your eyes please. Thanks. Okay, so some people haven't seen it. So proof by contradiction, right? We're trying to prove that this x is not rational. We're trying to prove that x is not rational. So we say, well, suppose x is rational. We start off from the opposite. We say, suppose x is rational, and we make a bunch of deductions. All these deductions, are logically sound. We see that from that assumption, we end up with something crazy. Okay. If we assume that x is rational, we end up with craziness, right? That we end up with these numbers that have no common factors, but they're both even. That's impossible. Okay? And so we say, okay, well, that must mean that our initial assumption was wrong. Right? That must mean that our initial assumption was wrong. Right? So x could not have been a rational number. Right? Assuming x was rational led to craziness. Right? So x could not be rational. End of proof. Okay. So that's how you do a proof by contradiction. Okay. Okay. Everybody else, any questions? So, okay. So the square root of 2. So the square root of x squared. So the square root of 2 is not a rational number. It's not a rational number. Okay. It's irrational. It's irrational. Okay. The book introduces one term, algebraic number. It's not that important to us, but let's just include it. So x is called an algebraic number. X is called an algebraic number if it solves a polynomial equation. Polynomial equation of the form a sub n x to the n plus a n minus 1 x to the n minus 1 plus a1x plus a naught equals 0, where all the coefficients are integers and n is some natural number. Okay, so
A0 is not 0. Isn't A0 not 0?
Wait,
A0 is not 0.
Why do you need that?
Never mind.
Is that part of it? I don't
Actually,
think so. But let me just go on and I'll see if I see it or not. Okay. So for example, this if we have x squared minus 2 equals 0, right? Then right, the square root of 2 solves this. Right, square root of 2 is an algebraic number. Okay, so you see, what are algebraic numbers? Well, roots of integers, roots of positive integers are algebraic numbers. Basically roots of polynomials are algebraic numbers. You might think that R is just Q plus all the algebraic numbers. Right? Like what's the difference between R and Q? That's what we're trying to talk about here. Right? And we see that, well, if you look at Q, it doesn't contain the square root of 2. Well, the square root of 2 is an algebraic number. Suppose we take Q and we throw in all the algebraic numbers. It turns out that you still don't get to R. Actually, you're very far away from R. Okay, so that's not what makes R. Right? That's not the thing that distinguishes R from Q. In fact, it's something much more subtle, and we'll try to head towards it. I don't think we'll get there. Yeah, Nick.
Can algebraic numbers exist within Q as well? Like, could you have 4 as an algebraic
sure.
number?
Yeah. So certainly, x minus 4, right? So 4 is an algebraic number.
Okay.
Yeah. Okay. So one problem of Q is that it doesn't contain all the algebraic numbers, but that's not the only problem. There's something more subtle that happens that we fix when we go from Q to R. Okay. I'm sorry. I was hoping to get to the rational zeros theorem today, but I guess we're out of time. Okay. So that's it for today.